Welcome back. The objective of this video is to explore the properties of logarithmic functions. We'll find the domain of a logarithmic function. We'll talk a little bit about general behaviors of logarithms, and we'll analyze a logarithmic function. We've shown that a log function is the inverse of an exponential function. So from our last lesson on inverses of exponential functions, we found that the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. So as we talked about, the x's and y's in a logarithmic function get switched with the x's and y's of an exponential function. And you may recall that the graph of an exponential function, just like a general y equals a to the some base x, appears something like that. So that might be like y equals 2 to the x. And it's going to go through the point 0, 1. That's going to have a horizontal asymptote at x equals 0. All of our range is all positive y's, and our domain is all real numbers. Well, a logarithmic function, if it's the inverse, then that information flips. 0, 1 goes through 1, 0. And a logarithmic function looks something like that. So this might be log base 2 of x. And that goes through 1, 0. And then our domain and our range, they flip. Our domain now becomes all real numbers greater than 0. And our range becomes all real numbers. So let's take a look at those properties. Properties of the graph of a logarithmic function, the graph of a log function. The x-intercept is 1, 0. We've got that there. The y-axis is a vertical asymptote. So we have a vertical asymptote now at x equals 0. We had a horizontal asymptote at, I think I said x equals 0. I should have said y equals 0. If b is greater than 1, our base is greater than 1, then the function is increasing. If our base is between 0 and 1, the function will be decreasing. The graph contains the point 1, 0 and b 1 and 1 over b negative 1. So this point here would be b1. And then 1 over b negative 1 is going to be, down here. The graph is smooth and continuous. It has no sharp corners or gaps. So we're going to go on to a couple challenging examples here. Find the domain of each logarithmic function. If we understand our transformations here, we know that this log function has been shifted 5 units to the left. So how is that going to impact our domain? Well, our vertical asymptote is going to shift 5 units to the left. So our vertical asymptote is going to come out here to negative 5. Instead of being at 0, and this point here, our 1, 0, is going to shift to negative 4. And our graph is going to look something like that. So the domain now is going to go from negative 5 to positive infinity. One thing to note is that x plus 5 has got to be positive. So the answer, log base answer equals exponent, the answer part has got to be positive. So another way to look at this is to say x plus 5 has got to be greater than 0. So x has got to be greater than negative 5. Which leads us to b, log base 3 of 1 minus x over 1 plus x. Since this fraction has to be positive, okay, so that must be positive. That means we're either going to have a negative divided by a negative, or it has to be a positive divided by a positive. So we can't have opposite signs in this fraction. So we're going to evaluate this a couple different ways, where we're forcing our numerator to be negative and our denominator to be negative, and we'll take a look at what those values are. So our possibilities are 1 minus x is going to be less than 0, and 1 plus x is going to be less than 0. So we're going to solve for both of these, and we get so solving each of these for x, we get x is greater than 1. An important thing here is the and x is less than negative 1. That's the only scenario where we could have a negative over a negative. Well, can x be greater than 1 and less than negative 1 at the same time? Well, the answer to that is no. So option 1 is not a possibility. That's never going to happen. So now let's take a look at option 2. Can we somehow get a positive over a positive? So can 1 minus x be greater than 0? And can 1 plus x be greater than 0? Can they, both the numerator and the denominator, be positive? Well, in this case, we'll get x is less than 1 and x is greater than negative 1. Well, that does exist. We can get an x less than 1 and an x greater than negative 1. So our domain in this is from negative 1 to 1. And on our final example C, we have the absolute value of x minus 2 has to be positive. Well, the absolute value is going to be positive. So we'll simplify this absolute value as we normally would. We'll say the absolute value of x minus 2 can be greater than 0, or the absolute value of x minus 2 is less than 0. And that will work just fine. So we add 2 to both sides, we get x is greater than 2, or x is less than 2, which essentially means we can use anything except 2. So our domain here is from negative infinity to 2 in union with 2 to infinity. In example 2, we're asked to match the graph of a through d to one of the following functions. F of x is log base 2 of x. That's going to be our typical logarithm function. That's going to be a growth function. And it's going to pass through the point 1, 0. So f of x is equal to graph C. So C is f of x. G of x, log base 2 of the opposite of x. Well, the opposite of x means we're going to have a shift along the x-axis. Our positive inputs will become negative inputs. So it's going to look a lot like C, but it's going to be over a reflection across the y-axis. So G of x is the graph of A. A is g of x. And that is a decay function. So this guy is decay. H of x, the opposite of log 2 of x. Now this is going to create a vertical shift. So everything that's from our standard logarithm, our positive y's are going to become negative y's. Our negative y's are going to become positive y's. So this one is b. b is h of x because we're reflecting across x. And then, so the last one, k of x, has got to be d. Again, log 1/2 of negative x. This actually is a growth equation, even though we have 1/2 for our b. Okay, so this is k of x. But essentially, the decay and the negative decay creates a growth situation. So this is a growth equation. Based on your findings, which graph above would also be correct for y equals log 1/2 of x? And that would be b. So g of x is also log base 1/2 of x. And I think I said, I did say graph B, but graph B is not g of x. Graph B is h of x. So let's go ahead and correct that. So h of x. So h of x, the opposite of log base 2 of x, is equal to log base 1/2 of x. In example 3, we want to sketch a graph of the parent function of log base 2 of x. Complete the table below. So when x is 1, so we want to get log base 2 of 1. What is the exponent that on 2 that gives us an answer of 1? Well, anything to the 0 power is 1, so we would get 0. And log base 2 of 2. What's the exponent on 2 that would give an answer of 2? Well, that is 1. And then log base 2 of 4. What is the exponent on 2 that would give an answer of 4? And so we have 0, 1, 2, and 3 to fill out our table. So now we can plot our points at 1, 0, 2, 1, 4, 2, and 8, 3. So there's a start of our logarithmic function. We can also do the same thing for the reciprocals, but our graph will look something like that. Question B asks, how is the graph of g of x equals the opposite of log 2 of x translated from f of x? Well, that negative sign, that's going to reflect over the x-axis. That's a vertical adjustment or adjustment to our y. So every positive is going to become, positive y is going to become a negative y. I may have missed that one. Here we go. And so there is g of x that might be labeled underneath my picture there. So we'll put it down there. Question C, make a table of values for g of x and graph it. Well, I've already graphed it. In our table of values, we said our positive y's would become negative y's. So write the xy rule. Our xy rule would just be x, comma, the opposite of y. So analyzing f of x, Our domain is from 0 to infinity. Our range is from negative infinity to infinity. The function is increasing and concave down. We've got a vertical asymptote at x equals 0. We've got an x-intercept at 1, 0. There is no y-intercept because of our vertical asymptote. And it's going to go also through the point 2, 1, or our base, which is 2, 1. And now we'll go ahead and look at g of x. And then g of x, our domain and range are the same as our domain and range for f of x. However, this function is decreasing. It is concave up because our rate of change is increasing. It may be negative, but it's becoming less and less negative, whereas in the other, our rate of change was decreasing. Our x-intercept still goes through 1, 0, but now we go through the point, our base 2, and negative 1. And again, we still have a vertical asymptote at x equals 0. And that wraps up this video on finding the domain and graphing logarithmic functions. And we'll get some more practice with this when I see you in class.